Okay, as I announced in the previous lecture, today's lecture 23, is the last one, last offline lecture, on-site lecture in this semester. Lecture 24 and 25 will be uploaded in its or their regular time slot. So please watch those videos, and I think that the most important thing for you to do right now is just to do your homework. No, your term project. So, as I told you, or as I discussed with you previously, so due date of your homework term project submission is December 22nd. So AM 8 o'clock. Please send me an email with your submissions. So do not use LMS system. There will be no link to submit your term project. So you must send an email with your video to me directly. So there is no delayed submission, so I do not accept any kind of any reason. So delayed submission. So please submit it on time. Okay. So do you have any question about homework? Sorry, term project submission or? Um,
So the next week we don't have any classes. The next week do we have online classes or offline classes?
no. So good question. So lecture 24th and lecture 25, that will be the last ones. And when we go to this week, uh, starting from 15th, that week actually is assigned to final examination for entire college. However, we don't have any paper exam in this class. No final exam, just to use this week to finish your term project. And your deadline is 22nd. So I think that maybe you may have some exams in these days, and now you can finish your term project. Okay, thank you for your question. And any other question about term project? So if you have any problem using this program or those programs, so please let me know. Okay, if you don't have any further question on homework, term project submission, so let me just start our last on-site lecture 23. Okay, so lecture 23 will discuss the concept or issues of a PMOSFET, especially in the most advanced technology node. So please have a look at this figure. So although we have 6 different lines, actually we can group them into 3 different lines. One is, so actually there is a pair, and there is another pair, and another pair. These pairs just shows that simulation and experimental result show good agreement. So for a while we do not care about simulation result, just treat them as one line. So you can find 3 different lines, and their difference comes from different surface orientation. So here and there and another one. So this is bulk PMOSFET and room temperature, and most importantly we just keep the direction of a channel. So direction of a channel is set to be 110, which is typical and almost universal in these days. Okay, so channel is fixed, and we just show the experimental result for 110 and other surfaces. For example, 001, and here you can see that there is a significant difference in their whole mobility. This is actually the inversion mobility, so not just the bulk mobility of our p-type silicon, but when we actually fabricate our p MOSFET with the different wafer surfaces, then we can have this different behavior. You can see that actually mobility of a 110 surface is somewhat higher than the other ones. So typically this 001 is the one used in our bulk MOSFET, planar MOSFET technology. So you can see that if we can change it to the surface direction to 110, then we will very happy. Actually, that happened in our previous cases. So previous technology FinFET really achieved this desire. So this one, this is channel direction, and channel direction actually it was 110, and yes, this direction is 001, and that direction, I don't know what exactly it's a sign, but it is a family of 110 surfaces. So that's the reason why if we use this FinFET technology due to its tall height, so you can see that the dominant side is not this 001 surface, but this 110 surface, and we obtained quite a high increase of p MOSFET performance. So now please have a look at this slide. This slide is just a stretched version of Intel paper. So this paper was published about 2009, around 2008 or 2009. At the time, still we didn't have a FinFET. So there was only planar MOSFET, and in the case of a planar MOSFET, but still they tried to do some calculation about different surface orientations. And actually the original version just have two graphs have a same height, but in order to match their different y-axis, I intentionally stretched this version for electrons. So please don't be fooled by different scales. As you can see here, electrons and holes, they show quite different scales. For example, if we have electrons, the scales goes up to 600. However, in the case of our holes, then it is just 340. So basically, electrons are showing much higher mobility in this case. Point is, here we have two different groups. One is blue one and one is red one for p MOSFET and n MOSFET. And please concentrate on the curves colored blue here and there. These are corresponding to the surface of 110 surface and 110 surface, and as I told you, this is corresponding to the side wall of a FinFET. So simply speaking, in the FinFET era, this blue curve was the dominant mobility curve for you. So please have a look at these lines. Even when we have 0 Pascal, no stress in this case, actually we can have whole mobility slightly lower than 190, and surprisingly, so the mobility for electron is somewhat lower than that number. So also if we introduce negative value of stress, it means that negative value means compressive stress, and here you can see, although they are drawn in the same way, but you can see that they are positively signed and they are negatively signed. It means that in the case of electrons or atmosphere, we have to introduce tensile stress to our atmosphere, and in the case of a PMOSFET, we must apply compressive stress. But anyway, you can see that here and there, these are curves for our FinFET error. Yes, surprisingly, holes shows even higher value, and if we apply, for example, a higher, I think that, this is wrongly drawn. For example, if we just concentrate on 1 gigapascal as a representative value, then we can have values like easily exceeding 200 square centimeter per volt second. So this is a quite good situation for our holes. Point is, now in order to have even better short-channel immunity, the technology has came back to this 100 surface once again in the form of so-called nanosheet MOSFET. In this case, instead of this shape here, instead of this blue fin, now we have the nanosheet laid in this way. So dominant surface is of course here and there. It is corresponding to this 001 surface. So that's the reason why now we have to concentrate on this lead curves. Then when you have a look at these lead curves, you can immediately understand the significance or severity of this problem. Blue ones shows more and less matched result. However, when you have a look at these lead curves, they really shows huge difference between electrons and holes. Their value start from higher than 200 and starting from 40. And when we successfully apply, for example, minus 1 gigapascal, which is quite a reasonable value, then we can have the value even lower than 140. For example, if we apply 2 gigapascals, I'm not quite sure that is matched or not, but still we have the values around 200. So simply speaking, as much as we keep this 100 surface for our PMOSFET, we start with losing whole mobility. So even though we can do our best to improve the whole mobility, but it never achieved the level of electrons even in its relaxed version. So that is a severe problem of NP unbalance issue. So previously, of course, when we talk about planar MOSFET, electrons or N MOSFET and P MOSFET were unbalanced. So everybody understood that situation, and they just to try introduce wider P MOSFET. So maybe you remember that if you study microelectronics or other courses, so you are taught to set wider P MOSFET to match it drivability of your N MOSFET and P MOSFET. That was planar MOSFET era. However, we have already studied the FinFET case. So in this case, actually, setting the effective width of your transistor inverters and inverter circuit, in order to control that number, then you have to control the number of fins in your circuit. For example, if you wanted to have a compensate the weak P MOSFET, then you must assign more fins for your P MOSFET and less fins for your N MOSFET. That is the typical way you do. The problem is now technologies are moving even more compact form of integration. So we are now trying to introduce so-called CFET. In this CFET case, N MOSFET and P MOSFET are not placed in a same plane, but they are vertically integrated. So previously, there is N MOSFET and there is a P MOSFET and P, but in the era of CFET, then this N MOSFET over P MOSFET, that is the way of integrating more transistors into smaller area. In this case, you have no freedom to change the width of your P MOSFET and N MOSFET independently. Just you have one single fin, quite tall fin. After that, by applying such a etching process, you make this CFET. So simply speaking, now we have no ability to control this effective width. However, the unbalance of electron mobility and hole mobility becomes quite big. So that will introduce a critical problem to our future technology. That is the main problem we are facing right now. So you know, Samsung and TSMC already announced their successful technology development for this nanosheet technology. However, it does not show that they completely solved that problem, and that will also make a big problem even when we come to this CFET era. So that's the reason why in this IDM 2025, so maybe next Monday, so we will have IMAX presentation here. And in this case, although the details are not shown to us, but it seems that they introduce two different wafers having two different wafer surfaces, and they just bond these two wafers and make a quite as a result of this bonding procedure, we wanted to make a quite complicated wafer by spending two wafers. And you know, it already have certain layers, so silicon germanium, silicon germanium, this kind of alternating layers, silicon and silicon germanium and silicon germanium. This kind of stacked layers are basic building blocks of our CFET technology. So now we are ready to make CFET. So since they have different orientations in this case and in this case, although they are bonded, they are coming from two different wafers, so they can enjoy different wafer surfaces, and expecting that we can increase the hole mobility selectively. That is the effort to increase P MOSFET mobility. So, what is your opinion? So, it is not, in my guess, I have no concrete information about this paper, but they do this job at the beginning of their processing. So there is no lithography on this structure. So it is a very early stage of fabrication. So maybe there is no worries about mismatches in the lateral direction. So we can just make a thick wafer, and actually this thick wafer, by eliminating this one, then we can make just a normal thickness wafer. And yes, so we are ready to start just monolithic CFET fabrication. But point is, this one already consumes 2 wafers, and so in the from the point of cost, so that will make obvious disadvantages, and I'm not quite sure actually industry will like it or not. It really depends on the actual numbers. So that is one thing we have. And I think that this is the last slide of our lecture today. So, as I told you before in this slide, so the wafer surface is really important, actually critically important to keep the PMOS as useful. So nowadays there are many other approaches to have one zero surface within this monolithic integration. So of course this one is quite a straightforward approach. However, in this case they do not want to use 2 wafers, just to use 1 wafer. Then how can we reveal this 110 surface? That is quite easy. Easy means that previously when we had FinFET, we used 110 surface. So simply speaking, if we just make a FinFET for PMOSFET, then that will give us 110 surface back. But you know, in the case of NMOSFET, still we wanted to have nanosheet. So that's the reason why people are trying many different variants. So I'm not kidding. This is the really happening in academia. So they named those approaches as tree-fed and fishbone fed. Well, I think that fishbone fed seems like a joke, but it's not. They are really serious about this one. What are they? Tree-fed. I think that due to historical reason, so this guy is called as tree-fed, and this guy called as fishbone fed. Their difference seems to be quite marginal. So the difference is whether they have the connection to this substrate or not. Even for PMOSFET, there is another suggestion that do not allow this kind of interbridge. So just have this 3 FET for P MOSFET side. But anyway, in this one, they suggest the combination of a 3 FET and fishbone FET. So simply speaking, it is not that difficult to make actually. So if we come back to our previous lecture material, so I'm not quite sure where do we have it. So why don't you just okay, that was a planar MOSFET, and when you go to 19, yes. So this is the previous lecture material for nanosheet MOSFET. So okay, there is a step called as a channel release. Channel release means that here, when you have a look at this one, this blue one is corresponding to the silicon channel, and green ones are silicon germanium with high germanium content. Then it is known that we can actually control the etching rate for silicon and silicon germanium, and usually silicon is not etched away. Only silicon germanium can be safely removed by certain etchant. So now we can completely eliminate this silicon germanium. That is quite a typical methodology to make this nanosheet. So when you have a look at this 3 FET or fishbone FET, you can see that actually there are remaining silicon germanium layer. Simply speaking, if we make an early stop of this silicon germanium etching process, then we will have the remaining structure. If we really want to make a nanosheet, then this is a failure. However, if we wanted to make this 3 FET or fishbone FET, then we can control this etch time, then just remain these bridge between two neighboring nanosheets. That is intentionally used to provide another conduction channel. So please have a look at this one. Let me just make even enlarged version. So now now you can easily understand this surface. Yes, this surface. Okay, so slowing down. This surface is really corresponding to. Well, what happened? Okay, a little bit slow, but no, this one is corresponding to the surface of 100. So I will just use this curly bracket, and here we have a newly introduced interbridge, and this interbridge has of course the channel. This is sidewall channel, and channel actually corresponding to that of FinFET. So simply speaking, it is corresponding to 110 surface, and we expect that since this is corresponding to 110 surface, may give us even higher hole mobility for this system. That is the main motivation of our FinFET. Of course, so in this case, the authors of this paper just introduce also interbridge to our N MOSFET. It means that their main motivation is not fixing this NP unbalance, but just to increase the effective width of this transistor. So simply speaking, let me just draw it. So if you have three different nanosheet, then what will be your effective width? So the sum of these three perimeter will be the effective width. But if we introduce this interlayer, then what we are sacrificing is this one, this one, this one, this one. These four line segments are eliminated from our peripheral length, but instead now we have so now we have additional these four line segments. So if we keep this interbridge height longer than this width or thickness of interbridge. So for example, if interbridge are tall enough, then this one is eliminated. Instead, this one is added. So in terms of effective width, it is a positive approach. So as you can see here, now you can see that this interbridge shows a little bit taller than the square. So this is tall and narrow one. So this is always good to have quite a narrow one, because actually in this interbridge, this thickness is used as fin thickness. If this is 6 or 7, then it means that we are now currently using quite fat FinFET, which is quite bad for short channel immunity. And if we have very narrow one, then that will be perfect for having short channel immunity. But of course, since the fin is too narrow, then we are afraid that the mobility of this structure is degraded quite significantly, because if we have too narrow fin, then now electrons or holes fill both sides of a sidewall, and their mobility is known to have drastic decrease according to the thickness. So it is known that actually the dependence is about power of 6. So if we, for example, if we introduce 2 times thinner FinFET layer, then it is expected that you have about 30 times reduction of hole mobility or electron mobility, so which is not acceptable at all. So that's the reason why we need to keep the fin thickness in a reasonable range. So now you understand the main weakness of this approach. So it looks beautiful. However, how can you control this with this WIB width of interbridge that is corresponding to the fin thickness? Then how can you control this one? In the case of a previous FinFET, you had patterning from top. You did a quadruple patterning. After that, using etching processor, you made these fields. There were certain lithography. Then how can you make this fin, internal fin? First of all, you make a wider fin corresponding to the nanosheet width, for example, 15 nanometer. And in order to achieve this for example, 5 nanometer thick interbridge, what you have to do is just to control edge of your silicon germanium area 5 nanometer and 5 nanometer from both sides uniformly, and stop there. If you make any mistakes in this case 1 nanometer mistakes, then what will happen? Then you will have just 3 nanometer or 7 nanometer. And according to this paper, if you make 2 nanometer difference in your interbridge width, that introduces real drastic degradation or improvement in their simulation in the device performance. So maybe you now understand this is quite tricky. Control of this interbridge thickness would be the key challenge for this one. There is no lithography, only etching control is quite important. And I told you that previously, a former time, one company, one industrial manufacturer tried to make a inner spacer, and quite similarly, when they make a inner spacer, they have to control the actuator of this inner spacer material, and if they cannot control that one quite uniformly, then inner spacer thickness can show some fluctuations. So I told you that for some time they gave up and tried to do without inner spacers. Of course, that was a completely failure. So simply speaking, if we adopt this kind of a procedure, then we must really careful about this etching process, and that will be quite difficult to control their thicknesses. So that is expected difficulties about this procedure. And please have a look at this simulated debug. So when you have a look at this one, please concentrate on differences in their scales. This left y-axis is corresponding to NFET. In the case of NFET, their debug shows just 4 millivolt per volt difference. And when you have a look at this right axis for P MOSFET, what is it? The difference is 15 millivolt per volt. Although they are drawn showing similar level, but actually this one is really marginal and this one shows this really drastic difference. For example, if we just align them all instead of using separate axis for this left one, so let me just draw it. Here we have a 50, 55, so where do we have 45? Yes, so yes, maybe we will have a 45 somewhere here. And our graph for NFET starting from 44.5 and end at 47. So we will have just this black line. This is the line for M MOSFET, and this one is the line for P MOSFET. What does it mean? It means that in this combination of tri-FET and fishbone FET, M MOSFET tri-FET shows quite good short channel immunity. But in the case of a P MOSFET, it is really awful in terms of short channel immunity. Of course, this axis is not channel length. Channel length is given as I remember that 16 nanometer, quite a reasonable value. But point is, now when we make certain change in this one, taller or shorter, it shows really drastic changes in this short channel immunity. So simply speaking, if we go to shorter and shorter HIB interbridge value, so it means that interbridge, just to introduce this small one, if we have this kind of shape instead of the desirable this shape, then it is quite bad in terms of a Dibble value. That is one. But question is, if we have the same value HIB, then what is the main difference between N MOSFET and P MOSFET? Do they have a different shape? Actually not. Both of our N MOSFET and P MOSFET shows this shape. The difference comes from the last one. This last one is not covered by gate. So you can see that here we have no gate. It is not covered by our gate in this way. That's the reason why this PIT FET shows quite bad performance compared with this P MOSFET or N MOSFET. So yes, so you can understand difficulty of this one. So also, we have to consider additional ones because now we have a combination of pure silicon and silicon germanium, silicon germanium, and what will happen if there are remaining certain germanium content and if it generates germanium oxide instead of silicon oxide, then that will introduce some problems in the device reliability. So if we use that device quite a long time, then something unexpected may happen if we have this kind of potential contributor to the defect. Okay, so anyway, this is I guess that as much as device architect is related, I think that this P MOSFET unbalance issue is as of today the most important one we have to solve. So what will be the solution? If you ask me to that question to me, so I have to admit that I have no clear idea about it. So similar ideas can be made, but what is the real practical solution to this problem? That is not that clear. But writing papers or publishing papers on this issue, that is quite easy because you can play with these tools and make many different ideas. But please be practical. It is really related with the future of electronics. So of course we are not in charge of developing that technology, but the community we are trying to belong to is really in charge of making the future of electronics, and they should make the right decision. And as a student or researchers in academia, we must provide some good advice on how can we improve the performance of these transistors. So if you search the web, then you can find so many fascinating suggestions, but can we make those devices without any difficulty? Do we have the manufacturability? That is the critical one. So please do not make a quantum jump to another new technology. Please be practical, and with minimal change of existing technology, maybe we can continuously improve the device performance. So sometimes how can I say, technology evolution is made by accumulating small improvement in small items. It does not completely change in our technology, but small portion, 1% to 2% differences can accumulate. Then we can have the real improvement. And it's not a solo play. So we means that the engineers all over the world are working together and competing to each other to solve that problem. So I'm quite optimistic about the future of a new architecture. Okay, so therefore now this is the end of our on-site lecture. So to me, actually, in this special topic was particularly difficult to prepare, because in many cases information about the actual device this is not disclosed. So I try to grab as much as I can, but maybe my lecture material may contain some wrong information compared with the actual reality in fabs. But well, I will just keep this lecture again and again and adjust this lecture material more close to the real one. Okay, so thank you for participating this very initial lecture, the first version. And as I told you before, so I will upload my lecture next Monday and next Wednesday. The topic will be the future of electronics. So, and another one Wednesday will be, I will just select one or a few good papers from IDM, and I will review them. So please watch those videos, and that will give you some clues about what is going on in this IDM. Okay, then do you have any question about lecture material or template submission? So if not, okay, then thank you, and let me just wrap up today's lecture.